Hello, everyone. Now let's begin this second class on analyzing. Okay, wait a second. Okay. Okay, now let's do this again. So, hello everyone. Now we're gonna begin on this class on the course on meta-analysis, and this class is gonna be specifically on how to extract data for your statistical analysis. But here's a problem. What happens if we want to do an analysis of overall survival? And when we're analyzing overall survival, we can all agree that we usually report mean, standard deviation, and sometimes they give us a median and interquartile range, and we can convert the median and interquartile range into a mean and standard deviation. We can all agree that overall survival would be um, a numerical variable. However, what happens if a study doesn't tell you the mean and standard deviation, doesn't give you the median and interquartile range, and it just gives you a graph like this, and it gives you a p-value? And as an example, this study didn't even tell us the mean and standard deviation of the graphs. It just gave us like, yo, it's different. Do you think we can analyze something like it's different for the statistical analysis? Or what would we have to do? What do you guys think? Can we analyze this, or we would have to um, exclude this paper? What do you guys think? Can we analyze this outcome if they don't give us a mean and standard deviation? What would we do?
No, we can't.
Okay. Anyone else think anything else different? Exactly. Like we can't analyze just colors, you know? Like this is a problem that we came upon particularly for the studies that are like focused on brain tumors, or basically any oncologic study, because what are the most relevant outcomes for oncologic studies? Those are overall survival, being how long they live after surgery or after diagnosis. So overall survival are one of the most relevant outcomes for oncological studies. However, they don't always like report the overall survival. And many times they'll just give us this graph. So what is this graph? This graph is a curve called the Kaplan-Meier curve. This is a time to event variable. What does that mean? That means it's a graph that tells us, oh, if at the beginning we have an example, 100% of our population, which would be this one, which basically means 100%, it's like the same. So if we begin with 100% of our population, and on the x-axis we have time, how long do they take to reach a specific outcome? As an example, in this study, we have overall survival. So we're analyzing when do they reach the outcome of dying. All right, when do they die? All right, but in theory, we could do an analysis like when do they progress? All right, like when do they either the tumor grows back, or when does the chemotherapy like stop working? Like any of these outcome can be analyzed through a Kaplan-Meier curve, you know. So this is a curve that we begin at 100%, and every time the curve decreases, it means that at any moment in time after we begin the study, a patient reached the outcome. So every time a patient dies or reaches an outcome, the curve goes down. All right. At 24 months, three patients died. It's gonna be a great decrease. If only one patient died, it's gonna be a small decrease. All right. So So the more steep a curve is, it means that the patients reach the outcome faster. So if it's like a nosedive, like it means that all the patients reach the outcome at a very small moment in time. If patients reach the outcome very slowly, that's gonna be a more horizontal line. All right, and usually this makes the test that's called a log rank test or log rank curve, which basically gives us a single p-value that tells us is it different or is it not different? And if it's different, it only tells us that, like, oh, there are differences between this and this and this and this. Which one's bigger? I don't know. It only tells us that they're different. So we would have to do like additional analysis to be able to actually evaluate all of these data points. All right. So far, any questions, any comments? All good? All good. Any comments, any questions regarding what a Kaplan-Meier curve represents? Good. Sweet. All right. So afterwards, you guys should also know that there's like a different kind of like there are a lot of additional data that we can add into a Kaplan-Meier plot. Like some studies, imagine that they lost follow-up of a patient. Every time we lose follow-up of a patient, that's what these crosses mean. So basically, they don't know if the patient died, but they lost follow-up of a patient. So that's what the crosses mean, all right? So just so you guys know what that means. And another important thing is that over here, they usually have a number at risk. So that is like really useful because it allows us to know how many patients begin from each specific group and how many patients like start losing at any specific time point, like 24 months, 12 months, etc., etc. So if I wanted to evaluate this as a categorical outcome, I could analyze it like, oh, how many patients of these reached 24 months, like a two-year survival, overall survival, like categorical value. But after this class, honestly, we will all love doing this because it's like the most specific type of analysis. So, what I'm gonna show you guys is how to extract data from like these types of Kaplan-Meier curves. Because imagine the problem that we came upon like a few months ago. Like imagine that we had these three studies. We had three studies that they all gave us Kaplan-Meier curves, but they didn't give us a mean and standard deviation. They just told us like, oh, these groups are different. All right. What were we evaluating? We were evaluating if patients who had supratotal resection, well, supramaximal resection, actually survived more than patients who underwent a maximal or a submaximal resection, right? Because there's a lot of controversy regarding if glioblastoma patients should undergo just a gross total resection or a supratotal resection. So after we finish resecting all of the tumor, a little bit over the margins, right? So they only gave us graphs. They didn't, they just told us like, oh, 9 months, and they didn't give us a 95% confidence interval. They didn't give us anything. Also, this other study also just analyzed the curves. This other study also just analyzed curves. So we're like, what are we gonna do? Do we just cancel this idea? No. We figured out a method to extract um, all the data points from these specific studies. And imagine that each study had like 300 patients. So at the end, we finished and we made like an Excel spreadsheet. It's opening. Give us a moment. Okay, look. We made a final spreadsheet with over 1,000 data points from all the previous studies. So what did we get? We got the category the category of patient that they were, either supramaximal or gross total resection. We also wrote down what study they came from, and then we wrote down at what moment they reached any specific outcome and how many patients reached it. All right. So if we had 3,300 patients, we needed 300 data points on when they found a specific outcome, which was either dying or another analysis on when they progressed. That makes sense? If we want to analyze 300 patients, we need 300 data points. All right? And after that, we put that everything into another statistical software called SPSS. So what we needed was, okay, a moment in time, and if they reached the outcome or they didn't reach the outcome. As an example, some patients, like, they'll just tell you, oh, they didn't die, they just survived up to the last follow-up. Oh, so in those patients we will just say, like, oh, at the end they didn't die, they just we just lost follow-up, so they didn't reach the event, but we will write down the last known follow-up. All right. So after that, we got 1,000 data points, dude. That is so big. Like, we would usually be limited, like, oh, we from each study we have one data point, which is a mean and standard deviation. But now we can extract patient data, specific patient data, from, like, just a graph, which is freaking amazing. So after that, what we did was analyze it, make a survival analysis, do a Kaplan-Meier curve. What is our event? Our time event is like the months. Overall survival is if they died or not. Which one was death? And after that, our groups were super maximal or gross total, and then we would make the option of making a survival analysis, and then we wait 30 seconds for Mr. SPSS to finish doing its magic, and boom, we have a hella big curve that we got from three images, you know? And after that, we'll get the mean, we'll get the 95% confidence interval, and we can report all of this data, and then we can get our Nobel Prizes, and then we can all go to San Antonio and then make a residency in the United States and make all the dreams come true. All right? So now we're gonna begin on how to do this process, all right? But is it clear what we're looking for? All good? Alrighty. So far this has been like theoretical. Now we're gonna begin with the fun stuff. All right. So I'm gonna pass you guys this document on. This is like a very friendly study to, like, do this as an exercise. So here's the thing: we wanted to analyze for another study that we're also, like, doing. What we want to analyze is, hey, if we have a stroke around tumor resection, does that affect overall survival? I don't know. Nobody knows, but we will know. So we have these Kaplan-Meier plots that begin at 100, and this is an overall survival Kaplan-Meier plot. Always when you want to analyze this data, you have to know what the graph is about, all right? Because this is the progression-free survival, which is defined as how long it takes for the tumor to come back, or for a patient to develop symptoms, or something like that. But this overall survival, this is just like death, all right? So you have to know what you're analyzing before doing your Kaplan-Meier plot, all right? So this is gonna be a Kaplan-Meier plot for one of the studies. And what do we need to do first? We have to get the highest quality image possible, all right? So we're gonna extract this. We're gonna take a really good screenshot of this. Boop. We're gonna know this is days. And after that, we have to know how many patients are in each group. So patients with ischemia and patients without ischemia. So patients that had a stroke around the tumor and patients without the stroke. The reason why I chose this study is because both groups had 46 patients. All right. Um, so that's really that's like simplifies it a little bit. So what we're gonna do is that I just shared you guys this site, which is like a way of easily extracting data from images. All right. So what we're gonna do is the recent screenshot that we did, which is this one. And now we're gonna point out what type of graph it is. We can also make bar graphs, which are way more simple. And there are a lot of different diagrams that this site can do. But right now, we're just gonna do a graph, a Kaplan-Meier plot, all right? So let's calibrate it. So to start this process, we have to calibrate it, all right? So it's gonna ask us, okay, first, mark your X on the X-axis. Um, what we're measuring, all right? So we're measuring days, all right? We're measuring days. Here's the beginning, here's a 0, and here's the longest point in our graph, which is 2000, all right? So this is 0, and this would be 2000, all right? And then we're gonna mark our y-axis, which would be over here and over here. So this is 0 to 1, all good. Now we finish our calibration, and now we can make a whole different kinds of stuff over this graph. We're gonna put add point. So this is everything you guys need to begin doing your data extraction of graphs, all right? So over here, we have the beginning, all right? So now, I like to like have this like as a beginning point just to like have a clear idea of where we're beginning. So now, we can only do one curve at a time. So we're gonna do patients with ischemia, all right? Patients with a stroke around the tumor, all right? So now we're gonna go to the first time it decreases. Because why? If we mark it over here, it'll make us as if nothing happened, all right? No change was done because we have the same number of patients. So when an outcome is reached, the line decreases as I just showed you. So over here where it decreased, we're gonna put the first event, all right? Always take advantage of this like zoom in um like this the zoom in graph. I'm gonna like actually make it way we can like make it like edit how many times we want to zoom. So it's like really cool, really, really cool, all right? So now, the next point is gonna be over here, then over here, then over here. So that's it. This is the magic. This is the magic. Are you guys excited? Are you guys having fun? Yes, we're totally having fun. No, let's be real, you guys. You guys are not having fun. All right. Yeah, this is like the part of doing studies that are like but dude, after you guys learn this, you're gonna have the edge over any other person that wants to do meta-analysis. Because, dude, everyone, if you guys don't know how to do statistical analysis, you can only do systematic reviews. And if you know how to do statistical analysis, you can do a meta-analysis. But if you can get like patient data from graphs, like you guys are just learning, there is no limit. The limit is your dreams and the sky. All right. Yep. This is it. This is why you woke up early on a Sunday, because we're marking points. We're marking points. We're having so much fun. So much fun. We're
Did
almost.
we mark all the? I have a question.
Yeah, of course.
Should we mark all the points?
Yes, only every time the line decreases, all right?
Okay.
Good.
Okay, good.
Yes. Almost done. Just kidding. We're not almost done.
First data and then the points where it decreases, right?
Yeah, exactly. Just where it decreases. Like you see that every time there's like a decrease, there's a beginning of the decrease and then a bottom point of the decrease. You only put it at the bottom, all right? All right. Okay. Oh, shit. Give me a second. Almost done. Almost done. Good. And now we're done. All right. That wasn't so bad. But now it gets worse. All right. Now we're going to view data. We're going to get a bunch of zeros and x's. And you're going to be like, ooh, this is so exciting. Now we're going to download it as CSV. And now, what are we going to get? In theory, we have 46. Wait a second. Where did it download? Give me a second. Dude, what did I do? Okay, here it is. Okay, I'm gonna open it in Excel. Now, what we just got are a bunch of X and Y's. So let's put like a little bit more spice in it. So the X, what is it? It's time. You see? That's why we begin with 0. X equals days. All right? So what is this? And what is this? This is the y-axis. What's the y-axis? It's the percentage of patients at any point in time that have not reached the outcome. All right? So at the beginning, 100% were alive. So 100% have not reached the outcome. And like at this point, in theory, we have a 0, which means that all patients died. All right? So in here, this is the percentage of patients alive. All right? So now you are just gonna copy paste this into your article and then you press the publish button and that's it. Just kidding. I wish it was that easy. Now the next point, what we're gonna do is okay, I don't care about percentages. I want to know how many patients are alive at any point in time. So what we need to do is start doing Excel magic. All right. So what is the Excel magic? The Excel magic means equals the number of patients in your sample, as an example, 46, yeah, being the original sample size of your group, times B2, which is the um n, which is the number of the percentage, all right? So now we're gonna copy paste into this. So this is super cool because, oh man, it's so noisy. I don't like this. I'm scared. Mama, come pick me up. What we're gonna do is like just like round down all these numbers, right? So we're gonna,
Wait, is that
yeah,
they
because it tells us like, oh, there are like 47.9 patients. But like we know that this 44.9 are actually 45, you know? Yeah. So what we're gonna do is like round C2. Oh, round C2, and then you have to know put how many digits you want round. And now we want 0 digits because we don't want any decimals, all right? So 46, and now we're gonna put it down, put it down. Good. So now notice what we got. We know that at 85 days, we have 45 patients. So that means how many died from the original 46?
One.
One.
Exactly. One died. Sweet. Now, um, we know that at 300 days, there were only 32 alive. We now know that at 100, 1,146 days, there were only 8 people alive. So that means that the other 38 died. Dude, this is so cool. So now, what do we need? We need 46 data points for these 46 patients. That makes sense? So we can analyze the data. Yeah? So now, what we're gonna do, we're gonna write down how many patients died. All right? So from here to here, 1 patient died. From here, 1 patient died. From here, 1 patient died. From 43 to 42, 1 patient died. From 41, 1 patient died. So what we're doing is like, oh, I know that at 144, 1 died. At this time, 1 died. At this time, 2 died. All right? So 1 died. So how many patients died between 39 and 37? 2 patients died, exactly. So, Diego, how can this be possible? That basically means that there was a moment where we had a big decrease. You see this big decrease? That basically means that 2 patients died at almost the same time, all right? So we have to take note of that, all right? And 1 patient died, 1 patient died, 1 patient died, 1 patient died. Between 33 and 32, 1 patient died, 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 1 patient died. Oh, 1 patient died. 2 patients died, 1 patient died. I tell you guys, like, if there's like a better way of doing this, I'm still like developing this. I have to do like 1,000 patient Kaplan-Meier curve. I have to make a better way for this, but I'll update you guys when I figure it out, right? Because dude, this was originally made by us. Like, I think this was only described like once in another paper before us, um, and then we're like, dude, let's get it, all right? And now at the end, notice that from 2, it stayed in 2. But what happened over here? What happened over here is that we just lost follow-up. So it didn't go to 0. It just stayed a little bit high. Okay? So here, we're just going to put 2. But notice that these patients did not die. These patients just lost follow-up. So this will be important in a few minutes. All right? So, all right. So now, how many data points do we have here? We have 38 data points, but we need 46. What happened? Because in some days, 2 patients died, all right? So we can't analyze this. We need specific data points. We need 1 data point per patient, all right? So what we're gonna do, and the last part of this class is, all right, here, 1 patient died. Over here, 1 patient died. Here, 1 patient died. Like in theory, we can like take all of the days that 1 patient died and just like copy paste them. But notice over here, this is different. Here, where 2 patients died, we're gonna do a double copy paste, all right? Because now we know that 2 patients died, so we need 2 data points, all right? So from that, all of the other days were like single patient deaths. Here we have 2 deaths. Here we have a bunch of single days. Dude, you guys are never gonna have someone like do the statistical process like right in front of your faces. Like, this is like, I really love when Pavel used to do this, just because I was able to like press pause in a recording and then go back to that. All right. So now we're just gonna copy paste this into this column, and now we're gonna sort them from smallest to largest. And now, what do we have here? We have 46 data points for 46 patients. So now we just violated the laws of statistics where they told us that a graph is only a graph, but now a graph are 46 data points, all right? So now we can actually get the mean and standard deviation with just a single button. We're just gonna put equals Mean, oh shit, I did some average, sorry. Average, mean, average from here to here. And that's the average. And then we can do equal standard deviation. And that's it. Imagine, this paper didn't even give us these details. So in theory, we wouldn't be able to analyze this data. But now we can make a standard deviation and mean, so we can put it into Review Manager for a future class where I'm gonna show you guys how to do like forest plots. That's gonna be like very soon. Or we can get the specific patient data that would only literally be relevant for outcome for survival analysis, and be able to make like a really high quality Kaplan-Meiers. Like, just as an example, very recently we converted one of our figures into this beautiful figure that is going to be published for the guys in Miami, right? So of course we all like pimp out images in Canva, but this is like really cool stuff. So what else? So yeah, after that, we in theory, if we wanted to analyze this like in in SPSS, what we need to do is put this as time in days, of course. Never forget it, what we're measuring. And then we would put outcome. 1 equals reached. 0 means not reached. All right? Because this is the way that SPSS analyzes it, all right? So what we remembered is that all patients reached the outcome except these that didn't reach the outcome. What happened to these? They just lost follow-up. So we can't say that they died, all right? Sweet. And after that, we would just put a group. Like, this would be very different whatever you guys are analyzing. Like, in this case, we're analyzing like super maximal, gross total, etc., etc. Oh, sorry, I was about to sneeze. Sorry. Um, so in this case would be like, oh, group, I don't know, one is super maximal. But in this study, one was stroke, all right? So in this case, these were all stroke patients, all right? So what would be next is going back to the next graph and now extract the patients without ischemia, all right? So we got our first 46 patient graph, now the next 46 patient graph, and then we would have two graphs, all right? So what I like to do is just have very separate each of our extractions. So this would be the study name, Theopold, and this would be stroke, overall survival. All right? And now we would do another graph saying, oh, now this will be Theopold, no stroke, overall survival. And this is where I would put the second graph, the blue graph without ischemia. Does that make sense? Yeah. It's just like a way of labeling stuff correctly. So what I just passed you guys is one of the graphs where I extracted all of these components for this stroke study. So I'm just gonna like translate this to English. So this will be days. This was percentage of population. This is patients alive. This is um round up. Oh dude, before this I didn't even know how to round up patients. I am so, oh no, this is not round up. This is a number of patients dead. Patients dead. And this is the new deads. Because remember that we need to know like, oh, two patients died, one patient died, two patients died, and this is like individual days. And at the end, this is how I got it, all right? So this is thepled ischemia, thepled PFS no ischemia, and this is like literally the way I did it, all right? So why did you have a different column for the days where two patients died? Um, we do this because wait a second, where did I leave my the one that I just did, the one that was the cleanest, right? So the reason why I do like two different columns, this is just to account for the days that two patients died, you know, and just to make it cleaner. But in theory, if three people had died in this day, what we would have to do if we would have to put like, oh, three patients died, three, 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 or just like three, like something like that. But like you have to keep track of the days where three people reach the same outcome, you know? Just so at the end you can copy paste them all into a single column, so it's easiest to put into SPSS or to do an average, you know? So this is just like for organizational purposes, you know? Does that make sense? What do you mean? I mean, these are both the same outcome because two patients died. I mean, the ones below. Over here? These?
Te puedo hablar en español, es que,
Ah, sí, date, date.
ajá, por ejemplo, donde tienes aquí el 1146
Ajá.
punto 1035,
Ajá.
pues a un lado tienes el 1800, entonces es lo que me causa
Ah,
duda.
este. Es que recuerda que esto no estaba así. Esto
Ujú.
está. Recuerda que al final hice algo que se le llama sort. Dame un segundo, dame un segundo. Ok. Lo voy a decir en inglés y luego voy a decir en español, ¿va?
No te preocupes.
Ay, espera, qué putas. Digo, qué verga. Digo, what the fuck. No me deja. Okay. One second, guys. I'm making a mess. Okay. Okay, okay. That's good. I reached it. Okay. Remember that at the beginning they were the same. Yeah? But what I did was like, oh, after I copy paste this, I'm gonna put them over here. I'm gonna put them over here. And now, no, I'm gonna do something that is called sort. Sort basically means like organize your values. So notice how they are the same, but now I'm just gonna sort them from smallest to largest. Because look, this is smallest to largest, but then when I copy paste it, this, even though this is like the largest, then it's another one small, then it's another one medium, then it's another one large, you know? So sort is just continue with the current selection so nothing else gets moved except from the things I'm highlighting. Sort just organizes them from smallest to largest, taking into account the patients that were repeated, all right? So sort, that's what messed up the values, but they are the same, you know? There were two 1,800, there are two 1,800. They are the same, all right? All right. So, en resumen, sí eran lo mismo, pero al momento de que lo pegué en una sola hilera y puse sort, es una manera de organizar la data y se organizó del más pequeño al más grande, y ahí es porque se organizaron los dos números, pero sí son lo mismo, ¿va? Entonces, tener dos columnas es más que nada para organización, ¿ok? All clear? All clear?
Mil gracias, Diego.
Okay, of
I
course.
have another question is about how you get the number of patients like right away with it.
Here,
In the C column?
here.
Yeah. Uh-huh. I forgot it.
Okay, it's the percentage, which was 100 at the beginning, and you multiply it by by the um by the original sample size. So if we begin with 100% of the patients, you have to go back to your study and see what was the sample size. Oh, it's 46 patients in this group. Oh, so it's gonna be 100% at the beginning, which is equivalent to 46%. All right. So afterwards, if as an example, here it's 50% of the patients are left. 50%. So that's 0.5. So how many patients are alive if we began with 46? Then 50% of 46. So we have to do the dreaded three number rule. All right? So that's just what we did. So we used to have 100% equals to 46 patients, and now we don't have 100%. Now we have 50%. So how much does that equal? 50 times 46 between 100. So that's 23. And that's it. So this whole column is like our column of advanced mathematics and rules of three. All right. So that's just the original sample size was what 46 times the percentage, which was the column that we got directly from the image analysis software. All right. Does that make sense?
Yeah, thank you.
And after that, we just round down the numbers so it's cleaner and round. And after that, we just write down the patients who died and stuff. All right. So that's how we do it. All right. All good. Any other questions? Any other comments? Andre, what's up?
Yeah, thank you, Dr. Diego. My doubt is, what about these little vertical lines that through the horizontal lines in the Kaplan-Meier are censored parts? I investigate in our censored parts, like censored parts,
Yeah.
but I don't understand. What about these patients?
Okay. Look,
Thank
in
you.
theory, the fact that they are censored in real life, it's a sacrifice. Um, you could do one or two things. Some people eliminate the patients that lost follow-up, but that like messes up your data. So what most researchers do is that they just mention, oh, we lost patients at this follow-up, but notice that the line doesn't go down. It's not like, oh, if a patient lost follow-up, that means they reached the outcome or they died. No, they don't do that because that would also mess up the data. So the sacrifice is, look, I'm gonna explicitly state when I lose a patient for follow-up, but by not decreasing the line, I am making a statement and a sacrifice saying, dude, I really hope that the patient that lost follow-up would behave or would follow the same trend as the rest of the patients that are not lost follow-up and I'm actually following. So it's like a sacrifice. So we don't like analyze those patients like as different because some Kaplan-Meiers like are different. Like um in these Kaplan-Meier curves, they state every single patient that was censored, but in this patient they don't. I mean, well, they do, but like the previous methods is like, oh, we can just accept that it's not gonna be perfect. It's just a reconstruction, but it's like the best thing we can do. So for the censored patients, we don't add like anything specific in the Excel sheet. We just accept that it's not gonna be perfect, and we just follow the same trend as if nothing happened. All right.
Okay, thank you. So
And
as you
that's
know, we accept that it's not perfect.
yeah, we're just gonna accept it and we're just gonna put it in the methods. Good. Any other questions? Any other comments?
So I have a question about the Kaplan-Meier curve you did first on SPSS.
Yes.
So it showed the median and the mean, but we cannot it show the 1 year survival, the 2 year survival in numbers?
There is a way to do it. I'm pretty sure you just have to like click a specific button. Honestly, I haven't done that. Like, let's do it. That sounds fun. If I'm not able to do it, it's just because I can't forget I haven't like forgotten the specific way to do it. Um, 1 minute survival maybe? No. Give me a second. I know there's a button on SPSS to do it. Ah, cumulative events, I think so. Okay. Let's see if that did something. But yeah, I would also want to be able to write that down. It's not telling it. It's not saying. Oh man. Okay. I'm gonna look up the button to how to do it. I can't like find it off the top of my head. I mean, I guess we can like no. I'm gonna look it up, all right? I mean, in theory, we can say like we can make a table by ourselves and say like, oh, by 10 months 90 people have died from our original 503, you know? Like that's a way to do it, but like there has to be a way to like make the table faster in SPSS. I'll look it up and I'll let you guys know and I'll update the class, all right?
Okay, that's great. Thank you.
Yeah, of course. Any other questions, any other comments, anything else? Does that make sense? Do you guys notice the power of this new statistical test? I mean, it's not new, but it's like really valuable. Another way that I found it useful is that sometimes, let me go to the DWI study. There have been cases where and this is like way easier, way easier. Okay, good. There have been cases where as an example, this is neurological deficits, all right? This is like neurological deficits, and they just tell us, oh, it's a different rate. And it's like, dude, what do you mean like there's a difference? Like, what are the numbers? We're not gonna tell you guys, we're just gonna put the p-value. So in those cases, it's also useful to like use this same software. We're just gonna load a new image. Um, and now we're just gonna put it like a graph. We're just gonna get calibrated. This is 0. This is 40%. 0. And this is 40. Calibrate. And now we can just do like rules of 3 because now we know that now we have how high these bars are actually. So this process is like really useful. And in this case, we would just do a rule of 3 with how many patients the original sample was and a rule of 3 with the new value. So this method has a lot of utilities once you know how to do the rules of 3 and how to use the software, all right? Any other questions, any other comments, anything else? If anyone recorded a Instagram story, you guys better like also tag me aside from med school mentor. Yeah, that stuff. All right. So, any other comments? Anything else? So, anytime you guys like want to try it out for yourselves, this is a really useful tool. I would highly advise you guys to try it out yourselves. So, like, what we would do is like English version. I'm gonna English data reconstruction. I'm just gonna upload the class later, but also I will also upload this last DWI example. So if you guys want to practice and be like, oh man, this is a really cool method, or maybe you won't use it until you actually need it for a study that you're making. But like if you guys want to practice, you can download the study that we just used in this class, which was Steepled et al. And this is like the original data extraction that I did, and you can try it out for yourself. Like, oh, I'm gonna try out the PFS, no ischemia, and if you get the same average and the same standard deviation as me, it means you did it correctly. All right. Of course, we can be open to like +1 or -1 days, just to make like an accurate estimate. Or of course, it's all like a pixel of difference. But like you can try it out yourself with these examples, all right? I'm just gonna rapidly like upload into our group chat just so it's a little bit quicker if you guys want to try it out. But yeah, any other comments? What do you guys think regarding this new method? It's cool, right? Kind of. It's just a new option, a new tool at the end of the day, all right? Again, checking the chat, checking the chat. It is very cool, Yara. All right. Then, if we're all done, I'm gonna stop the recording.